everyone, today we are going to investigate the time bandwidth product. So let's say we have x of t, something like this. So the variance of t can be calculated as the integral of t squared, absolute value of x squared dt, over the energy of the signal. So this expression can be seen as the energy weighted variance because this is the instantaneous power and this is the energy. Alternatively, we can see the absolute value of x of t squared normalized as a probability density function. So then it's clear that this is the variance of t. Now let's take the Fourier transform of f. By the way, in this calculation, we assume that t has zero mean, just for simplicity. So after we take the Fourier transform, the variance of f is given by the same expression, f squared x of f squared df over the energy in the frequency domain. So using Parseval's relation, we know that x of t squared dt equals x of f squared df, which is the L2 norm squared of the function x. So in both cases, the denominators are the same. Now let's look at the numerator over here. So this numerator is equal to taking the inverse Fourier transform of this part gives us d dt x of t absolute value squared times dt. Again from the Parseval relation. Actually, there's a factor here that we forgot. So let's take the Fourier transform of this, which gives us 2 pi j f x of f. So we should square this one. Absolute value squared gives us 4 pi squared f squared x of f squared. But we don't have 4 pi squared here, so we divide this part by 1 over 4 pi squared. So now let's replace this numerator by this new expression. So we get the variance of f is equal to 1 over 4 pi squared integral of d dt x of t squared dt over the norm of x squared. So remember that we are looking for the time bandwidth product. So let's multiply the variance of time and the variance of frequency together. So what do we get? In the denominator, we get the norm of x to the fourth power, and in the numerator, we first have the t part. This part didn't change. And now we have this second part over here. d dt x of t squared dt. And we have a factor 1 over 4 pi squared. Okay. So now we notice that this part is actually the norm squared of t times x of t. And this part is the norm squared of dx dt over 4 pi squared times the norm of x. So notice that we are multiplying two squared norms with each other. Here we can use the Cauchy-Schwarz inequality. The norm of the inner product of a and b squared is less than the norm of a squared times the norm of b squared. Okay, so then we can write the variance of t times the variance of f squared is greater than the norm of these two things. The inner product of these two things, of course. So the inner product is given by tx of t, first of all, this part. And then we need the conjugate of this part. So we can write dx conjugate of t dt times, since we are taking the integral with respect to t, dt, all squared. Now remember that the absolute value of the real part of a is always less than the magnitude of a. So we can write, instead of this expression, the magnitude squared of the real part of this integral, real part of this whole integral. Okay. Remember that the real part of a is equal to a plus a conjugate over 2. So is greater than 1 over 2 times, first of all, a itself. So t times x of t times dx conjugate dt plus tx conjugate dx dt. Here, remember that t is a real variable, dt. We can simplify this part by getting t outside and writing this as d dt of x of t times x conjugate of t. And this is simply the magnitude, the absolute value of x squared. So again, this expression is greater than, here we had this 1 over 4 pi squared, which we forgot over here and also here. So again, let's add that to here as well. Now we got 1 over 8 pi squared times also here we had the norm of this expression squared. So here we need the norm of this part squared and the absolute value of this part squared. So actually we get let's rewrite this. We get 1 over 16 pi squared times the integral of t times d dt, absolute value of x of t squared times dt. Now we can actually evaluate this integral. Oh, and we also had this in the denominator, which we also forgot. So the norm of x to the 4th power, the norm of x to the 4th power, and here also the norm of x to the 4th power. Okay. So now let's evaluate this integral. We can call this part u and this part dv. Then this is equal to u times v evaluated at minus infinity and infinity, because this part is obviously minus infinity and infinity, minus v times du dt, which is 1. Okay. Now remember that we here assume that this value is finite. So this actually means that this integral here we have a constant. We assume that this integral is also finite. So for this, the value as t goes to infinity of t squared, this expression inside the integral, must go to 0. So the same is true for minus infinity as well. So this part we can ignore. This goes to 0. And our expression becomes 1 over 16 pi squared, 1 over norm to the 4th power, absolute value squared of this expression. Well, this is the norm of x as well, squared. So as you can see, this part cancels with this part. And we find that the multiplication of the variances is greater than this. So taking the square root of both sides, we get this expression. And we can look at this as delta t, and this is delta f. So this is a time bandwidth product. It's greater than 1 over 4 pi. Let's write this for the angular frequency as well. So the angular frequency is equal to this. So we can write delta t delta omega is greater than 1 over 2. Okay, so now let's find which function satisfies this equality. Well, to find this, we should go back at the place where we used the Cauchy-Schwarz inequality. So here it is. Here. We use this and this as the two vectors. So for equality to be satisfied, these should be proportional or quote-unquote parallel to each other. So let's write this equation. T times x of t is proportional to dx dt. Let's solve this differential equation. T dt. Yes, so we get from here ln x equals 1 over alpha times t squared over 2 plus a constant, which gives us x of t equals e to the t squared over 2 times 1 over alpha times e to the c, which we can call a constant a. So this is our solution. And for x of t to be bounded, we need alpha to be negative to get finite energy. So we have found that the Gaussian function is the optimal function with the highest time bandwidth product possible. So now let's switch to quantum mechanics. We know that the eigenstates of the momentum operator are plane waves. So P is an eigenstate of the momentum operator, and taking its inner product with x gives us a plane wave. So let's say we have an arbitrary state phi. So its wave function in the momentum space is given by phi of p, which is equal to this expression. Here we use this identity. The sum of these outer products is equal to the identity matrix. So phi of p is equal to dx times, notice that we have here this expression, which is the complex conjugate of this expression. So we can write e to the minus ipx over h over the square root of 2 pi h. And this is 5x. Actually, let's make this phi prime to distinguish between these functions. Notice that this is like the Fourier transform. So let's put this into a more familiar form to see the relation between x and p more clearly. Let's call p prime equal to p over h bar. So let's replace all the variables accordingly. So this part becomes p prime h bar equals the integral of e to the minus I p prime x over 2 pi h prime, 2 pi h bar times 5x. So this is like the Fourier transform of 5x. Let's put these constants to the other side. Actually, let's put these. Phi of x e to the minus I p prime x dx. As you can see, this is the Fourier transform of 5x. So here, p prime corresponds to omega that we previously had, and x here corresponds to time. However, this is the momentum actually, and this is the position in quantum mechanics. So previously, remember that we derived this expression. We derived this. So now let's write the same thing for p prime and x. Actually, p prime is momentum multiplied by a constant. So delta p prime, delta x is greater than 1 over 2. And remember that delta p prime was equal to delta p over h bar. So we can write delta p delta x over h bar is greater than 1 over 2, and we get the familiar uncertainty principle between the uncertainty in momentum and in position.